Okay, this is section 4.6, decimal adder. Computers or calculators perform arithmetic operations directly in the decimal number system represent decimal numbers in binary coded form. An adder for such a computer must employ arithmetic circuits that accept coded decimal numbers and represent results in the same code. For binary addition, it is sufficient to consider a pair of significant bits together with the previous carry. Decimal adder requires a minimum of 9 inputs and 5 outputs, since 4 bits are required to code each decimal digit, and the circuit must have an input and output carry. There is a wide variety of possible decimal adder circuits depending upon the code used to represent decimal digits. Here we examine a decimal adder for the BCD code. Okay. Let's see. Consider the arithmetic addition of 2 decimal digits in BCD together with an input carry from previous stage. Since each input digit does not exceed 9, then the output sum cannot be greater than 9 plus 9 plus 1 equals 19. The 1 in the sum being the input carry. Suppose we apply 2 BC digits to 4-bit binary adder. Okay, the adder will form the sum in the binary and produce a result that ranges from 0 to 19. These binary numbers are listed in the table down below and are labeled by symbols K, Z8, Z4, Z2, and Z1. K is a carry, and subscripts under the letter Z represent weights 8, 4, 2, and 1 that can be assigned to the 4 bits in the BCD code. Columns under the binary sum list the binary value that appears in the output of the 4-bit binary adder. The output sum of 2 decimal digits must be represented in BCD and should appear in the form listed in columns under BCD sum. Problem is to find a rule by which a binary sum is converted to the correct BCD digit representation of the number in the BCD sum. Okay. They come up with the this right here that shows the condition for correction and output carry can be expressed by this Boolean function. When C is equal 1 is necessary to add that's weird. C waiting room. Hi, Britton. Would it not let you in? That's weird. Yeah, on my end, it popped up and said that you were in a waiting room and asked if I wanted to admit you. Yeah, I've never seen that. Interesting. Hope that's not a sign of things to come and I got to admit everybody. Okay. So down here, let's see. We got our add-in, login coming in. It's going to our 4-bit binary adder. And we got our carry in coming in here, and then our carry out. That K you see right there represents the K from this formula. Z8, Z4, Z8, Z2 are coming out of this binary adder. Now Z8's coming in here, Z4's coming in here. This is the Z8 and Z4. That's the second term right here. Our last term, Z8, Z2, We have Z8 coming down here. We have Z2 coming in here, so they're coming into an AND. And they're all three of these, the K, the Z8, Z4, the Z8, Z2, are coming into an OR gate, so that's the plus between them. And then that's going out to our output carry, which is this right here. Specifically, though, notice that the output carry is branching off down into here as these Z8, Z4, Z2, and Z1 are coming in to a 4-bit binary adder. And then we got a 0 that's coming in here to help control the results. So that's a BCD adder. We're not going to spend a huge amount of time on that. These are just giving you examples and how they can be implemented. Okay. Binary multiplier. Multiplication of binary numbers performed in the same way as multiplication of decimal numbers. The multiplicand is multiplied by each bit of the multiplier, starting from least significant bit. Each such multiplication forms a partial product. Successful partial products are shifted one position to the left. The final product is obtained from the sum of the partial products. This is what they're referring to here. Multiplying those two get together. So for example, if I had 1 times 1 0. B1, B0, this would be our try it again. I don't know why I'm losing half my screen sometimes. B0, yep. Okay. And this is A1. A1 and A0. So 0 times 1 is 0. 0 times 1 is 0. And shifting this over, 1 times 1, 1. 1 times 1 is 1. Adding these, I get this. Double check this. I'm not that good with multiplication. This is 1, 1, which is 2 to the 0, 2 to the first, that's 3. So that's decimal to 3. And this is 2. 3 times 2 is 6. This is 2 to the 0, 2 to the first, 2 squared. That's 4. 4 plus 2 is 6. Okay, so that's what they're talking about. Now, this part right here is A0. B0, A0, B1. That's just to indicate when we're multiplying together. A0, B1. I guess I don't even look that. A1, B0. This is A1, B0. And this one is A1, B1. And that's where they get this notation from. And then they label each one of these. This is P0, P1, P2, and I don't have it because I don't have a carry. But if I had added these and I'd end up with like 3, for example, put a 1 and you carry 1. So in my case, that's 0. Okay, so they're indicating that you could use this kind of setup to come up with a multiplier. I wish that would go away, but oh, there it goes. Okay. Nothing exciting on this. What world is that? Okay, so I guess just moving my mouse off that's why I can't point to it. That's B0. I'm gonna point to it anyway. So this coming in here, this is A0, A, B1, and that is an and that's our A0, B1 right here. And then this one is A0, B0, which is this one right here. This one is A1, B1, which is this one right here. This one is A1, B0, which is A1, B0, which is this right here. We talked about adders, so they're not going into the detail of what's involved there, but you're adding A0, B0 is not going into an adder because it doesn't have to. Because this is automatically coming straight down here because there's never anything here. So it'd be nothing to add together. This one here, we're sending this into a half adder. So we're taking the results of A0, B1, A1, B0, and that's coming into a half adder and giving us P1. And then the carry, if there is one, comes over here. I didn't have any carries in my example here, but again, if I add these together and it gave me 3, then I'd put a 1 and I'd carry a 1 over here. So that's what this carry is coming across here. And we're adding the result here. Let's see. That's this one right here. And notice here we had 2 of these coming in. I only have 1 coming in here because notice that this is blank. So you'll ever have is 1 here. And notice that there's no carry coming out of this because there's no way you can have a carry. Because there's not like another place to carry it to. But the outputs of this will give us P2 and P3. Does that make sense how that works? Okay. I don't know if I could do a 3-bit if that become too complex or not. But if I had, let's see, B0, B1, B2 times A0, A1, and A2. So I multiply these together. That gives me A0, B0. Multiply this times this, that give me A0, B1, and A0. Now let me start over. If I can move that or not. Poor planning. B0, B1, B2, A0, A1, A2. Those represent ones and zeros. So multiply these, that gives me A0, B0, A0, B1, A0, B2. Then I'd skip this, come over to this spot, and I take A1 times B0, A1, B1, A1, B2. Then I'd skip 2 spots for this one, and I'd have A2, B0. I'd have A2, B1. And I'd have A2, B2. And add these together. This is going to give me my P0. This will give me my P1. This will give me my P2, P3, P4, and then possibly our carry of P5. So that'd be kind of our setup. How do they have it? A0, A1 coming in from the side over here. Okay. Okay, and the B's, they're just having them come in wherever is appropriate. Okay, and then P0 is the far one. Okay. So P0 will be A0, B0. See, it's coming in like that. And then B0 is coming in to an AND. That's going straight down to our P0 there. And that's this. And then here I have A0, B1. Probably a clever way to do this. That's my A0, B1. And this is A1, B0. So A1. Seems bad to keep putting these separate. That's coming into an AND. That's our A1, B0. That's this one right here. And then we want to add these together. So coming into our adder. Let's get. And that comes out and gives us P1 carry. Because remember this, if I add these two together, that could potentially have a carry comes over to the next one. Carry on the bottom side, not that matters. Bottom, okay. And then I'd come over to our next adder. Now I'm not going to have room, but you see the idea of how to build that. Now here's a clean way to do this, I guess. Well, this has 4, doesn't it? 4-bit by 3-bit binary multiplier. So again, same principles kind of holding true here. You know, they've figured out what do they need to multiply together, and then go into an adder and so forth. And they haven't shown all the details. They're implying that all of these are coming in here, which is true. But each one's going into the adder maybe at different times. You know, they're not all being added together like this. Or maybe they are. I haven't written this all down. Maybe it does come out that way. A0B3, A0B2, A0B1, A0B0. No, these 3, maybe all these coming in. They show you a picture of that. Okay, 4.8 magnitude comparator. Drink here. I find this interesting. How they came up with the that you could do voltage to represent A is greater than B, A is less than B, A is equal to B is just fascinating to me. Makes sense when you're a computer programmer. You know you're using those. You know everything gets converted to voltage. You know everything's going through circuits inside the computer and so forth. Okay. Comparison of two numbers in operation that determines whether one number is greater than, less than, or equal to the other number. A magnitude comparator is a combinational circuit that compares two numbers, A and B, and determines their relative magnitudes. The outcome of the comparison is specified by 3 binary variables indicate whether A is greater than B, A is equal to B, or A is less than B. On the one hand, the circuit for comparing two n-bit numbers has 2 to the 2n entries in the truth table and becomes too cumbersome. Even with n is equal to 3. On the other hand, as one may suspect, a comparator circuit possesses a certain amount of regularity. Digital functions that possess an inherent well-defined regularity can usually be designed by means of an algorithm. A procedure which specifies a finite set of steps that if followed gives a solution to a problem. So if you can come up with that algorithm, then you can probably program it or put it into a circuit or whatever is what they're indicating. Okay, you got our two numbers down here, each with 4 digits. So that's what this is talking about. Let's see. When numbers are binary, the digits are either 1 or 0. And equality of each pair of bits can be expressed logically with exclusive NOR function, as this. So this exclusive NOR gives us our x by's. The equality of two numbers, A and B, is displayed in a combinational circuit by an output binary variable that we designate as by the symbol A equals B. The binary variable is equal to 1 if the input numbers A and B are equal and equal to 0 otherwise. For equality to exist, all x sub I variables must be equal to 1. Because if you think about it, 1 and 1 and 1 and 1 and is multiplication. We think of it that way. And the only way they can give you 1 is if they're all equal to 1. So that's what they're indicating to you. And that's again based upon this up here. The less than, or the greater than, sorry, A is greater than B is represented by this right here. The A is less than B is represented by this. And see, to determine whether A is greater than or less than B, we inspect the relative magnitudes of pairs of significant digits starting from the most significant position. If the two digits of the pair are equal, we compare the next lower significant pair of digits Comparison continues until a pair of unequal is reached. If a corresponding digit of A is 1 and that of B is 0, we conclude that A is greater than B. If the corresponding digit of A is 0 and that of B is 1, then we have A is less than B. And that's easy to remember because, well, 1 is greater than 0, A is greater than B. And here, if B is 1, then B would be greater than A. Okay, they show the setup here. So we've got our A3 and A4. Now notice that those are branching down, but they're also going through inverters because for the x sub I, we need A and B and we need A prime and B prime. Specifically, it's A and B and not A and not B. And then there's a or between them, a plus. So this is just what this is doing. So A's coming in here and did I read that wrong? Okay, they're not implementing this. Well, I should be able to see that, but I'm not. Hmm. Where in the world did I put my logic sample down here? I guess I have it right down here. You can see it. Okay, so let's look at this first. A, B, prime, B prime. Okay. So this one is AB Okay, so I need two products there. A, B, and I need A prime, and I need B prime. Then there's a plus between them. Okay, so I got that. That's not what they're saying down below. They're saying, okay, A, inverters, inputs. Okay, and let's go all the way across. Okay, so this has two and. Okay, so two and they're going into this is saying A or A prime B. So A prime and B are together. A prime B are together. And B prime and A must be together. Those are each coming in to there, and okay. Hmm. Should have listed all the possibilities, but I think I've covered them all. Okay, they're right. It's the same thing. Seeing it. because they gave us up here for x sub I. But then what they implemented was we paired these together. Okay, so that's our x3, x2, x1, x0, just based upon those coming in. And then our a is equal to b is just the anding of these. So a is equal to b is down here, and we have 4 inputs coming in here, and x0, x1, x2, and x3. And then again, this gives you your 1 or 0. It gives you voltage, but that indicates whether they're equal or not. Okay, so then for the less than case, what they're implementing is this right here, a prime b, or yeah, a prime b. A prime b, okay, that's coming off this line right here, so that's a prime b. And plus x3 a2 b2 prime x3. So that's probably this next line here. Maybe not. What in the world is that one? That is that's a2 prime b2 and x3. Hey, I don't want to do all of them. I'm gonna paste. But I'm having trouble seeing it. This one right here is coming in from here. This A2, or this coming down here is X3. Okay, where was I? Okay, X3. This is coming in here as an AND coming from here, which is this AND, which is A2 prime, and this is B2. Which is this I guess I was looking at the wrong one. X3 A2 prime B2. Okay. Then that's this line right here. This next line is coming from here. And what is this? This is X3. What's that? It's coming in from there, X2. This is coming in from this AND right here, which is A1 prime, B1. X3, X2, A1 prime, B1. Okay. Does that make sense on how to interpret those? So we'll trust that everything's correct on there. But all they're doing there is implementing these. And we could do that ourselves now that we know the formula for X3, you know, how they crisscross like that. I'm not sure the benefits of actually sending that through that technique versus just simply implementing this. Because this would be two AND gates and an OR gate for each X. Wait a minute. No, I still have to do two inverters here. So I don't understand the benefit of using our exclusive NOR circuit. But anyway, that's how you do the comparison. Let's see. Boy, it's just not. What in the world is that? Okay, I guess we're ready for decoders. Okay, 4.9 decoders. Discrete quantities of information are represented in binary additional systems by binary codes. A binary code of n bits is capable of representing up to 2 to the n distinct elements of coded information. A decoder is a combinational circuit that converts binary information from n input lines to a maximum of 2 to the n unique output lines. If the n-bit coded information has unused combinations, the decoder may have fewer than 2 to the n outputs. The decoders presented here are called n to the m line decoders, where m is less than or equal to 2 to the n power. Their purpose is to generate the 2 to the n or fewer min terms of n input variables. Each combination of inputs will assert a unique output. The name decoder is used in conjunction with other code converters such as BCD to 7-segment decoder. And this example is considered the 3 to 8 line decoder circuit, figure 4.18. That'd be this right here. 3 inputs are decoded into 8 outputs, each representing one of the min terms of the 3 input variables. 3 inverters provide the complement of the inputs, and each one of the 8 AND gates generates one of the min terms. Particular application as decoder is binary to octal conversion. The input variables represents binary number, and the output represents 8 digits of a number in the octal number system. However, a 3 to 8 line decoder can be used for decoding a 3-bit code to provide 8 outputs, one for each element of the code. Okay. They're just indicating here that you're having your Z come in here, Z prime, Y prime, X, and X prime. And if you remember from when we were working with the min terms and max terms and so forth, remember we had X prime, Y prime, Z prime, X prime, Y prime, Z, so forth. Our primes is where is equal to 0, and where it's not prime was where it's equal to 1. So these can be represented with this kind of setup. And that shows you the outputs that come from it. And it shows you a 2 to 4 line decoder. I wish they'd give an example. It's pretty obvious to see this. How can you change from binary to octal using this? Because if this is binary, that does not equal this in octal. I can see how the connection would be there. This is D0 through D7, which is what our octal is. Oh well, I guess I don't worry about that. Everything was ones. That would be, assuming this is one number. 2 to 0, 2 to the first, 2 squared. It's 4, 6, 7. So that'd be 7. I mean, this would be 6, which is 1 there. This would be 5, which is a 1 there. And so I see the pattern there. I just don't see how that corresponds to octal. Huh, yeah, I don't know. Okay. This next one. Some decoders are constructed with an AND gate. Since an AND gate produces the AND operation with an inverted output, becomes more economical, generates a decoder minterms in a complemented form. Furthermore, decoders with an enable input constructed with an AND gate is shown in this figure. Circuit operates with complemented outputs and complement enable input. The outputs of the decoder are enabled when E is equal to 0, active low enable, as indicated by the truth table. Only one output can be equal to 0 at any given time. All other outputs are equal to 1. Okay. The output whose value is equal to 0 represents minterms selected by inputs A and B. Circuit is disabled when E is equal to 1. So the E is where you're passing in voltage to enable the circuit to turn it on or turn it off. That's not quite correct because even when it's off, there may be a low voltage going through. Regardless of when the circuit is disabled, none of the outputs are equal to 1, none of the minterms are selected. In general, a decoder may operate with complemented or uncomplemented outputs. Enable input may be activated with a 0 or 1. So since E is coming into each or I guess the inverted E is coming in each one of them. So if you pass in 1, enabled when E is equal to 0. So if I pass in a 0 for E, it's coming down here, becomes a 1. And since it's passed into each one of these, then that's like 1 times whatever's there. So it doesn't change it. But if you pass in a 1 here, that inverts it to a 0, and each one of these is coming in as a 0. And just thinking of the and itself, 0 times anything is 0. So it shuts them all down. Since each one of these is 0, then the inverter changes these to 1s, and they're 1 straight across. And the x's here represent when you put a 1 in for E, it doesn't matter what A and B is, because 0 times anything is 0. And then it shows all the truth tables when you plug in all those other values. A decoder with enable input can function as a demultiplexer. Circuit receives information from a single line, directs it to one of 2 to the n possible output lines. Here's a 4x16 decoder constructed with 2 3x8 decoders. So we got our X, Y, Z, and W inputs coming into this decoder. We also have them branching off and coming into a second decoder. So we got our 4 here, and then since each one of these coming in here, that's where we get our 16 at. D0 to D7 and D8 to D15. So D0 to D15 basically. Okay, W, I was wondering why W had an inverter on it. W is our enable, I think. W is equal to 0. Top decoder is enabled, and the other is disabled. The bottom decoder outputs all zeros, and the top 8 outputs or generates our minterms. And W is equal to 1. Enable conditions are reversed. Okay. So this W here is our enable. So our 3x8 decoders here, having our 3 inputs coming in, and then our enable, like that. Okay. Let's see. I got time for that. I guess combinational logic implementation decoder provides the 2 to the n minterms of n input variables. Each asserted output of the decoder is associated with a unique pattern of input bits. Since any Boolean function can be expressed in sum of minterms form, a decoder generates the minterms of the function together with an external OR gate that forms a logical sum, provides a hardware implementation of the function. In this way, any combinational circuit with n inputs and m outputs can be implemented with n to the 2 to the n line decoder and m OR gates. And again, they don't show you a lot of the detail here on these at this point. Since they've talked about it earlier, they just talk about just in general. Since we got 3 variables, the x, y, and z, coming in there. And remember, if we were to go through and build our table, so forth, Says we obtain the functions for the combinational circuit in the sum of min terms form. S is going to be our 1, 2, 4, and 7. And C is going to be our carry. And it's 3, 5, 6, and 7 coming out of it. And of course, this one branches because we use 7 in 2 places. And that comes from our truth table of full adder to build these. I think that's pretty much it there. So let me just show where they're getting that from. It doesn't show us the truth table. Oh, there it is. Truth table. Remember, over here is where we got our X, Y, and Z, and then our carry and our S, and where we built our X, Y, and Z down here. And everywhere we had a 1 for like the S, then we would put a 1 in our table. Like here, 0, 0, 1 was 0, 0, 1, and we put a 1 here. I can't show it right there. So again, where they're getting that from then is, how they came up with that. Is that go away? There. I'm not sure why that's popping up now. Does that make sense? Okay. So the next thing we only got 2 minutes, so I won't go into it. But next thing we'll look at is the encoders, which is right here. And a lot of this goes a lot faster here at the end because we're not actually doing the entire part. We're just looking at what the geniuses in the past have been able to come up with. So we'll start with encoders on Monday then. I'll go ahead and stop the recording.